Okay, you have questions on homework? Which ones? Okay. 4 on math. Anybody have the math?
I have 4 years of math.
Okay. Number 4. So it says x dot y dot vector is equal to this matrix t squared 0, 0 t. What? Times x y vector. Where x0 is 1 and y of 1 is 10. So I can multiply out this matrix and rewrite this as a system. X dot is equal to xt squared and y dot is equal to yt. And so I'll do the x1 first. So dx dt, well, I'm going to separate variables. So dx over x is equal to t squared dt. Integrate both of those. So natural log of the absolute value of x is equal to t cubed over 3 plus c1. So natural log of 1, so now I'm using the boundary condition. Natural log of 1 is equal to 0 plus c1. So c1 is equal to 0. So now we have natural log x is equal to t cubed over 3. And take e to the power of what's on both sides, and you get x is equal to e to the power of t cubed over 3. And then the y equation says dy over y is equal to t dt. So natural log of absolute value of y is equal to t squared over 2 plus c2. And then the boundary condition for y says if t is equal to 1, y is equal to 10. So natural log of 10 is equal to 1/2 plus c2. So c2 is equal to natural log of 10 minus 1/2. So natural log of y is equal to t squared over 2 plus natural log of 10 minus 1/2. take e to the power of both sides, and you get y is equal to e to the power of t squared over 2. This is all 1 power plus natural log of 10 minus 1/2. And by the exponent rules, that's e to the t squared over 2 times e to the natural log of 10 times e to the natural log, times e to the negative 1/2 power. And that is equal to 10 times e to the power of t squared minus 1 over 2. Mm-hmm.
You did something where it was plus C2,
Mm-hmm.
but then you brought that in front of the e power before solving.
Okay, so if I would have gone straight from here, I would have gotten a function, so natural log of y, because we're dealing with positive y's, is equal to t squared over 2 plus c2. And then before I go to the boundary conditions, take e to the power of both sides here. We get y is equal to e to the t squared over 2 times e to the c2. And e to the c2 is just a new constant, so y is equal to, I'll call it c3 times e to the t squared over 2. And then you can use the boundary condition from there. Right. Yep, that's right. Yep. Yeah, exactly. Any other questions about the homework? Yeah. I just I dropped the absolute value because the boundary conditions were positive, so I just took it as a function that's dealing with positive y's. Mhm. Mhm.
So because you say express it x dot y dot, you assume that x is a function of y is a function of t. Is that it?
That's right. And in dynamics, okay, yeah, that's true. That would in dynamics, x and y are always, so this is a differential equation. In this class, x and y are always positions, and they're always functions of time. So so this u vector is equal to xy for the x component, xy squared for the y component. Like you said, we're going to assume that x is a function of time and y is a function of time. So ddt of the quantity xy is, so this one we have to use the product rule, x dot y plus x y dot. And ddt of the quantity xy squared is we have to use the product rule, and we're going to have to use the chain rule on this one. So x dot times y squared plus x times that should be so now x times the chain rule says we're going to take the derivative of y squared with respect to y times dy dt. So that's equal to derivative of y squared with respect to y is 2y. So this is 2x y y dot. And I did that with the equals. And so as a vector, that's the x component is x dot y plus x y dot, and the y component is x dot y squared plus 2xy y dot.
The question I have is, there's like a million different ways of writing vectors and different formats of writing. Do you care which ones you prefer, one over the other, as far as
If
IJK or matrix?
I like it in this column matrix form. I don't think I would probably mark you off for not doing it that way, but the benefit of that is then you can use rotation matrices, multiply vectors by rotation matrices to re-express them in different coordinate systems. I'm trying to think if that comes up all the time in D form. I'm trying to think if that comes up in this class. I think I'd probably talk about it a little. I think you could probably get by in this class with any of those formats. But
Yeah, it's better to do it in this format, obviously.
I like it in that format because your calculator understands how to do vector operations in that format, and for multiplying vectors by matrices in the future, it's sort of a practical way to do it. So yeah, I guess I would recommend do it that way. We will have a couple times in this class where it makes more sense to think about it in terms of a magnitude times a unit vector I plus a magnitude times a unit vector j, blah, blah, blah. So, we'll use that when it's useful. But most of the time, this is, I think, the most practical way to do it. Any other questions? All right, so we finished last time with the chain rule thing for calculating acceleration. So given the velocity as a function of some position variable, we would calculate the acceleration as dv dx times dx dt, and this is just a velocity component. So now we're going to extend that a little bit. What if instead of being given the velocity vector as a function of x, you're given the object's path as like a function of x. And its speed is a function of x. And say we still want to find the acceleration vector as a function of x. So for example, let's say that an object moves to the right along the path y equals cosine x. And let's say the speed is constant. So with a constant speed of 1 meter per second. What's the acceleration as a function of x? Well, you can approach this the same way every time you see it. So step one, we want to find the v of x as a function of x, given the path and the speed. And that's going to be equal to the speed times a unit vector tangent to the path. This is the speed. So to do that, step 1a, first you have to write the path of this object. You have to parameterize this path in terms of the variable you're given. So the position vector, yeah, any problem like this you can solve with these steps. So the position vector as a function of x, well, we know that y is equal to cosine x. X is playing itself. So as a vector parameterization, this is just going to be x cosine x. Anybody remember? I think maybe this would be Calc 3. 4 weeks ago? Yeah. So the part of Calc 3, anybody remember how to, what we're trying to do, that's a parameterization for this object. So at any given x value, that's the position vector. The parameter is x. How, from there, do we come up with a vector that's tangent to that path? That's always a good guess, but yeah, if you take the derivative with respect to the parameter, it'll always give you a vector tangent to that path. So DD parameter of the position vector gives a vector tangent to that path in the direction of increasing parameter. So what does that mean, in the direction of increasing parameter? Well, that's a rhetorical question, so don't talk. Just kidding. Okay, so there's the path. Taking the derivative of that position vector with the parameter, say, and evaluating it here, gives you a vector that's tangent to that path. Here's a line that's tangent to the path. My next try, I'll do it. But a vector has to choose one of those two directions. Which of those two directions is it going to give you? It's going to give you the direction that you move along this path as that parameter increases. In this case, our parameter, in the example that I gave, the parameter is x. And so the vector is going to be in the direction of increasing x that way. And there'll be problems where it says that the thing's moving in the direction of decreasing x. It's still on this path going the other way. Then your unit vector is, you're going to have to multiply -1 to your unit vector. Okay, so going this way. But that's not a unit vector yet. So step 1b is to normalize that vector. So let's say that the vector you get out here is u. Okay. So the vector you get out of step 1a is this vector u. So how do you normalize that? The unit vector in that same direction is equal to 1 over the magnitude times that vector. On a TI-89 and probably an Inspire, but I'm not sure about that.
Oh, it's really easy on the Inspire.
Of the, and that calculates the unit vector in the direction. Yeah, okay. And on the 89, that's the one I'm familiar with. There's a function called unit v, and so you take the vector from here, just plug it into unit v, and it'll do it for you.
So parameter, you mean the x?
In this case, it's x, but it doesn't have to be x. Yep. With, that's right. Yep. I'll do that example I gave. Right. And then you just have to make it a unit vector. And then step 2, well, then you multiply by the speed. So I guess, so step C, 1C, your velocity vector as a function of x now is speed times the unit vector you just calculated. And now that you have velocity as a function of x or whatever position variable, step 2 is just doing what we did before. The acceleration as a function of x is dv dx times dx dt. Okay, so the example that I gave above, I'll go through that. So our parameterization in terms of x of the position vector is x cosine x. And so a vector that's tangent to that path is 1 negative sine x. So that's a tangent vector in the direction of increasing x. Is that a unit vector? No. So now the magnitude of u is 1 plus sine squared of x square root. And so the unit vector is x over this radical negative sine x over this radical. This is increasing x, so now we have to ask, is this thing moving in the direction of increasing x or decreasing x? And it says it in the problem. It's moving to the right. So the object is moving to the right. So this is what we want. And so the velocity vector as a function of x is this times the speed. The speed was just a constant 1 meter per second. So this is the velocity vector. And so now this is the step where things can get pretty ugly. In my notes it says dot, dot, dot. I'm not even going to do it because I'm too lazy. But so now the acceleration, you can and see how it goes. I mean, I think the thing is, like I'll always give you ones that I'll give you a shortcut out of painful differentiation because I don't want you to spend a quarter of a test just taking a long derivative, you know. So the acceleration is dv dx dx dt. Dx dt is the x component of the velocity. And what's the x component of the velocity? Yeah, the x component of what I have written right above. So that's x over 1 plus sine squared x.
The derivative is x, right?
The position, yes. If you take the derivative of x with respect to x, you get 1. But to get the velocity, that's the derivative of x with respect to time, and that's a totally different thing. So that's why we have to go through all this, is because we don't have it expressed explicitly as a function of time. If you know your position vector is a function of time, then just take one derivative and you're done. If you don't know the relationship between position and time, then you have to use this chain rule idea.
Unit is x. Wouldn't that be 1 over the square root of 1 plus sine?
Yes, thank you.
Yeah, that's what I.
Oh, okay.
I think that's where you're going with it.
Oh, okay, okay.
Right.
I see. Thank you. I know. That better not look messy in your notes either when you turn in your binders. Yeah. No, nothing crossed out. What? I don't need this. From the peanut gallery. I get enough of this at home.
Most of us are that same mistake. Would it just be dy over dt at the very end there? Then you
Which one?
your v.
At the very end? So the dv dx, you have to take this. Yes, that's not so horror. Yes, the y one is pretty ugly. So that one's not so bad, but this one, you have to use the product rule and the chain rule and whatnot. It's okay. I mean,
That's a 1.
The red one.
thank you. Any other questions about that one? Okay, so if you see a problem where you're trying to come up with acceleration and you have a way to get velocity as a function not of time but of x. I mean, if you have velocity as a function of time, then that's easy. You just take the derivative with respect to time. If it's with respect to some position variable, you know you're going to have to use this chain rule thing. And in my experience, there's always some people where I'll set out a problem like this and they'll just think to themselves, derivative of velocity is acceleration, and they'll take one derivative and be done. And you can't do that, so don't let that person be you. Yes? You would differentiate this vector with respect to x. Multiply, yep. Times this expression. That's right. Any other questions? This is what it says in my notes. And I stand by that. Yeah. Okay, so let's talk about circular and spherical motion. So what this means is an object moving an object moving, I don't want any scribbles here either, at a fixed distance from some point. If it's moving in (2D), that's circular motion. If it's moving in 3D, that's spherical motion. In either case, over an infinitesimal time interval, dt, that motion is circular. So even if over finite times it's moving in 3D on a spherical surface, if you limit the time down to 0, you limit towards a case where the object is moving in a circular path in a single plane. Okay. And in that plane, over that interval dt, the object rotates through some infinitesimal angle change d theta. Then the angular velocity vector and that's lowercase omega, is defined as, let's call it an absolute value of an absolute value of a magnitude scalar omega times a unit vector. Not always u, but it always has the hat. The hat is what makes it a unit vector. Where the absolute value of that scalar omega is the absolute value of d theta dt. And u is perpendicular to the plane of the circle according to the right-hand rule. So say that something's moving in a circular path like this. Where the coordinate system is this. Then right-hand rule goes like thanks. It does look like it. Sort of looks like Quasimodo's hand or something. At any rate, so the fingers are the circular path. Yeah, it's like I've never thought about that. People would understand that better if I just said like hold a beer in your right hand. Your fingers are making the circle and the beer is pointing as a yeah, you can bring in one page beer. Cheat sheet. Okay, so your fingers are doing this, your thumb's doing this. So what's the direction of that unit vector, or what would be the components of that unit vector? 0, 1, 0, exactly. Okay, so here's another example. So let's say question? Yep. Yeah. Okay, so let's say that an object moves at 1 revolution every 2 seconds. And the direction of the rotation, if the coordinate system is this, say there's a line at 45 degrees, and the object moves in circular motion around this line. What's the angular velocity vector? Well, one revolution every 2 seconds. Yep, it's along that line away from the origin. That's right. So the unit vector is cosine of negative 45, sine of negative 45. That's the unit vector, and that's equal to, and actually, these are pretty much always going to end up in 3D, so let's just put the 0 on there. Negative 0.7071, negative 0.7, nope, dx is positive. Y is negative 0.7071, Z is 0. One revolution every 2 seconds. What's that in radians per second? So it's 2 pi radians per 2 seconds. So pi radians per second. So the angular velocity vector is equal to, so that would be, this is square root of 2 over 2, right? So we got square root of 2 pi over 2, negative square root of 2 pi over 2, 0 radians per second. Any questions about that? So I guess on Friday I'll find angular acceleration, and then I'll give you the equations, the vector form of the circular and spherical motion equations. You've seen these before, that velocity is equal to angular velocity times r, and acceleration is equal to, the tangential with its formula and the centripetal with its. But we're going to use a full vector form where you don't have to think about directions. The directions all come out for you. Okay, that's all.